Mike sent me this little blurb at the top. So he received his PhD under Hans Bethe at Cornell University in 1959. He was a postdoc at Princeton at the Institute for Advanced Studies and at Columbia, and then he was at Columbia and Stanford before coming in 1966 to UCSC to initiate and participate in the development of the physics department here. And I joined the physics department only in 1973, so I'm an old timer here, but a relative newcomer compared to Michael. He worked in many areas of physics and is a master in many areas of physics. He became an emeritus professor in 1994, but since then he's still been extremely active, especially in history of physics, where he's contributed major work, especially on Newton and Hooke, but also more recently on 20th century history. And he received the highest award in the University of California for an emeritus professor in the area of humanities and social sciences, which is quite unusual for a physicist. I think Mike is probably the only example. It's an award that's only given once per year, I think. Now, Michael has contributed to many areas of physics, far too many to go into any detail, but I just wanted to give you a little bit of a flavor. So, all textbooks on quantum field theory discuss the Knoste-Lee-Nauenberg theorem, which Michael proved with the famous Nobel Prize winner T.D. Lee. This is the theorem that says that quantum field theory, gauge theories, are infrared finite. All such theories have what we know as infrared divergences. So when you take into account the emission of massless particles like photons, infinite numbers of them get emitted, and if you try to calculate any of the relevant Feynman diagrams, you always get infinity. And what the theorem proves is that all those infinities cancel for good physical reasons. So individual calculations give infinite results, but when you take them all together, the signs are such that they always cancel and the results are always finite and physical. When I was an undergraduate, I was tremendously inspired by reading and working through The Theory of Fundamental Processes by Richard Feynman, the first of his many popular lectures. This one is actually meant for advanced students. And Mike and Peter Carruthers were the physicists that took the notes. Many of you have heard great things about John S. Bell and his tremendous contributions to understanding quantum mechanics. Well, Mike worked with Bell, and the third of the papers in the collected papers by Bell about quantum theory is The Moral Aspects of Quantum Mechanics by Bell and Mike Nauenberg. So I want you to have some sense of who you're hearing from Mike. Mike is your chance to interact at only one stage removed from some of the giants of 20th century physics. So this is the abstract that Mike sent me of his talk that he's about to present. So what he says is that he's going to explain the connection between classical and quantum physics and the particular example of Rydberg atoms, which he will explain to you. The hydrogen atom, of course, has an infinite number of energy levels. The lowest level is called n equals 1. The n equals 2 level is a good deal higher and closer to being unbound. The transition from n equals 2 to n equals 1 is the Lyman alpha transition, beloved of all astronomers. If you go up to levels like hundreds, n equals hundreds, then it's called a Rydberg atom. And because you're very close to the Rydberg energy, 13.6 eV, which is the binding energy of hydrogen. And so Mike solved an interesting problem that helps us understand the classical quantum transition. And then he says that he's also going to discuss the relevance to Bohm. And in fact, he's going to argue that this means that Bohm's interpretation of quantum mechanics is not tenable. And I haven't heard that part, and I'll turn it over to Mike.
Thank you very much, Joel, for your introduction. I can say it's about the nicest introduction I've ever received. I appreciate you doing a little backtracking. I am, very grateful to you for this. I regret I wasn't able to be here at the first session, because at the time I was in Copenhagen attending a festivities for Bohr's 100th anniversary of the discovery of the Bohr atom. We had lectures there similar to those here at the Academy in Copenhagen, and later I gave a lecture at the Bohr Institute. So what I'm really coming back to is comment that the relevance of my talk will be the relevance to the first session on the foundations of quantum mechanics. And as you can see here, and as Joel says, I've been very much interested in the history of physics, because I think it really illuminates very much how we got from there to here. And as you can see from a little ditty that was actually recorded and noted by Felix Bloch in a Physics Today article. Irving with his psi can do calculations quite a few, but one thing has not been seen, just what does psi mean? In other words, this is right at the beginning when Schrödinger announced his wave function at a lecture. Schrödinger at the time, it was clear that what it meant was already a problem. And let me be very brief. The problem was vastly discussed by all the founders of quantum mechanics. And by the time that I was a student, and as Phil says, I had the privilege of having some very good people teaching courses in quantum mechanics, including Hans Feder, Feynman, and others. There was no measure, nobody ever talked about the measurement problem or any difficulties. I mean, we all felt that physics was well understood. And it wasn't, in fact, until I met Bell some years later at we both were in Slack at the time, that he began to argue with me about foundational questions that I had not been aware of. And during our discussions, we eventually ended up writing what I consider a tongue-in-cheek article about the measurement problem that you have all heard of. According to von Neumann, there is an endless chain that never seems to end into a measurement. And we ended up with the joke that in the end, you know, maybe it's when you read the article in Physical Review that the wave function finally collapses. I don't believe a word anymore of what we said at the time when we were young. But, you know, John Bell, I think, continued to believe there was a problem. I don't think there's a problem. And the problem is when you don't see a problem, it's very hard to worry about the solution. I like we put a little footnote there to illustrate how little anybody cared about this, is that most physicists who were called attention that there was a difficulty thought, well, the difficulty has already been resolved by Bohr and everybody else. And in a few minutes, if I could spare a few minutes, I'll tell you how the difficulty is resolved. Well, things have dramatically apparently changed, as you heard during the first week, I believe. Although I was not here, I did take a look at some of the videos. There's a vast amount of discussion going on, and in particular, various suggestions are made. Everett, multi-universes by Bohm and others, and so forth. I will only comment at the end about Bohm's and de Broglie's interpretation. But let me start with the problems as they were seen at the very outset, because it turns out that Schrödinger, being a young man at the time, well, let me get rid of this.
Then just click on play.
Yeah. Schrödinger was a young man. I think he was a postdoc or had a position in Zurich. And Peter Debye was a senior faculty in physics at the ETH, and he invited Schrödinger to give an account of de Broglie's ideas of relating particle momentum to wavelength. And Schrödinger actually gave a very nice account by noticing that if you assume that the number of wavelengths for a circular orbit is finite, so that there are no interferences by the waves going around and around.
You meant to say it's integral.
The sum is an integral, right? So it says the sum would be an integral. So this was the Broglie, and this was the contribution at a seminar that Schrödinger gave. And the story, which by the way is told and it's transcribed in Physics Today by Felix Bloch, who was attending the lecture, is that Debye, waved and said, Schrödinger, you really, this is sort of childish. Why don't you write down an equation? I mean, that's how we do physics. An equation to represent what you've done. And Schrödinger went off, and the story is that he went off skiing, not with his wife, but his mistress. These are the legends, rumors. But he came back and asked Debye if he could give another lecture. And at that lecture, he said, Debye, at the last lecture, said that I should write an equation, and here is the equation. So within the weekend that he spent skiing, he came up with probably one of the most significant equations in terms of physics. Now, Schrödinger being a young man, and in the old days, young people were very respectful. They consulted with their senior colleagues or with the experts, and he was worried. Here is an equation that gives interesting results. I can calculate, for example, the levels of the hydrogen atom, and I get the right result. But what on earth is psi? And so who is he going to consult? There was two people who were the absolutely senior people to consult with. One of them was Lorentz, who was the senior physicist in Leiden. You all know about the Lorentz transformation, but Lorentz is much more than that. I mean, he really was the sage. So Schrödinger wrote to Lorentz, and I don't have time, and I don't really suggest that you read everything, but this will all be, available online. The main point that Lorentz pointed out to Schrödinger is that if you want to interpret, as Schrödinger thought, that his wave function, somehow the square of the wave function represented the density of mass and charge of the electron, then Lorentz said, look, you're in trouble because the darn thing spreads. And, basically it's unavoidable. It's unavoidable. Blurring a wave packet does not seem to be very suitable for representing things which you want to ascribe rather permanent individual existence. I mean, there were by then numerous experiments that showed that the electron behaved as a point particle and there was no blurring. So something about Schrödinger's interpretation of the wave function being a density, the square of it being a density, didn't act together. But Schrödinger shot back another letter to Lorentz and said, no trouble, I just worked out a particular case, namely a wave packet in the harmonic oscillator, and you know what? It doesn't spread. Wow. Lorentz was really impressed. He said, this is marvelous, I mean, this goes against all expectations that there is no spreading when you have a wave packet, contrary to all my intuition. But then he said, maybe this is a special case, and you ought to consider, the real problem, which is the wave packet in the presence of an inverse square force, which is Coulomb force or gravitational force, and then you will see that it will spread. And Schrödinger admitted that well, he didn't quite admit. He said he can foresee with certainty that similar wave packets can be constructed which will travel along Keplerian ellipses for high quantum numbers. However, technical computational difficulties are greater than the simple example given here. In other words, he was unable to solve the problem of what happens to a wave packet when you have the real problem in hand, namely the hydrogen problem. And when I found this out, and you know, I looked at my textbooks and so forth, and I found out that nobody had, not only they haven't bothered to solve the problem, they don't even talk about it. And in fact, to the present day, you can look at textbooks in quantum mechanics who never address the problem of what does a wave packet do in the presence of an inverse square force. And there seems to be very little interest in the subject either, which puzzles me, because the first thing you would like to see is how does the classical world that we are accustomed to emerge from quantum mechanics. I mean, we should ask not how do planets move around the sun according to Newton's equation, but how do they move around the sun according to the equation of Schrödinger, if that's the fundamental equation. And you wave your hands and you go, oh, you know, I know the Ehrenfest theorem, I know the mean motion is classical and so forth. But there's much more to it than that. I mean, if the wave packets are spreading, you know, how fast do they spread, how much do they spread? All kinds of questions that you reasonably should ask. But anyway, you know, you look at your standard textbook and you say, oh, you know, correspondence principle, I look at high quantum numbers, and lo and behold, there should emerge elliptical orbits. Well, you know very well that that's not the case. And why? And in fact, if you don't get elliptical orbits by going to high quantum numbers, how do you get them? And that was a problem that I set myself to work out. And you know, it was worked out successfully. And I will try to describe it here. Because there are two reasons. It teaches you a lot of lessons about the question of what's the meaning of psi. What is the meaning of the wave function? I'm not going to get into deep issues of measurement and all that. Leave that to the philosophers who will be able to resolve it. But we want to know what is in what sense does the wave function give us the observations at the classical level, and also, you know, there's a lot of hand waving about a quantum classical divide, and you know, quantum mechanics, you know, works up to a certain level, and then the classical world comes out. Here's a simple example. You can work everything out from scratch from the beginning, and that's how we do physics in general. We work, since Newton himself said, you know, you work out the simplest example, which is the hydrogen atom. You work it out in full detail in the new theory, and you see what's going on. So whatever you have intuitions, or whatever your preconceived ideas are, we do physics by making observations, and I will tell you also about experiments, and by looking at what simple examples teach us. So here's what Max Born had to say. Born had the right idea in how to interpret psi. And this is worth really reading, so I will take a few minutes to go over it with you. It is misleading to compare quantum mechanics with deterministically formulated classical mechanics. Instead, one should first formulate the classical theory, even for a single particle, in an indeterministic classical manner. Now, what did he mean by that? You know, you think of classical physics is totally deterministic. Initial positions are given, and we calculate or we compute to arbitrary precision, or we think arbitrary precision, but Bohm was very wise in pointing out that in reality we have to measure the initial conditions and we have errors. So there are errors in the initial conditions. In a single particle moving around the Z over r square, there is an error inevitably in your apparatus to measure the initial velocity and the initial position. And so the question really is, how does that error propagate? I mean, this is one of the things that when I was a student wasn't taught to me. And as you know, it was only in the late 1970s that we became aware there was a really tremendous fault in classical mechanics not to be aware of the fact that there are uncertainties in any measurement. And these uncertainties don't necessarily remain small. And that, of course, is the whole business of chaos and so forth, is that the uncertainties can become large uncertainties. So Bohm was right on the ball in pointing out that the way to compare quantum mechanics and understand this relation to classical mechanics is to first formulate classical mechanics in also in a statistical way. And of course, that means solving the so-called Yuval equation. The Yuval equation gives you the evolution of a classical system where you can input the uncertainties and so forth. And this is what I'm going to be addressing today. And Bohm concludes that, you know, there may be, certainly if you go to very long periods, there is a critical moment where this ceases to be true, that there is any kind of precision in the predictions and it becomes statistical in reality. Now Schrödinger, I think throughout his entire life didn't like the interpretation, right? I mean, he put Bohm, he said, God knows I'm no friend with the probability theory. I've hated it from the first moment our dear friend Max Born gave it birth. For it could be seen how easy and simple it made everything in principle. And I will show you that in principle it makes things very simple. And I'm a very simple guy, so I like simple things. I don't understand complicated things. Everything ironed out. And then he ends up saying the true problems are concealed. Well, that's of course what these lectures are all about. Now, some time ago, I published an article which appeared in Scientific American with two collaborators who are experimentalists in Rochester who did experiments in the so-called Rydberg atom. With Rydberg atom. A Rydberg atom is when you basically take an electron that's in an inner orbit and you kick it to very high quantum numbers. And there is where you expect to see classical behavior. And here is just a page where I want to illustrate my solution of a stationary solution of the Schrödinger equation, which you won't find in the textbooks. This is the square of a wave function for an eigenstate of the Hamiltonian. It's not, however, your garden variety eigenstate of fixed angular momentum or fixed. So what is it? I mean, its behavior is easily understood if this is the center of force, and this is a distribution, a stationary distribution of particles going about the center of force, which is 1 over r squared. This is a stationary solution for a mean principal quantum number n equal to 40. And as you can see, when the particles are close to the closest to the center of force, in astronomy we call it perihelion, then of course the probability of finding them there is smaller. When they are at aphelion, the probability is large, and this represents very nicely a stationary distribution which we can actually understand from a classical point of view, but this is a solution or an eigenstate. Now you say, well, how come you got this eigenstate? This isn't the eigenstates in the textbooks. Well, remember that the eigenstates in the textbooks are highly degenerate. You have a degeneracy for a principal quantum number, the angular momentum can have values from n, from L equal to 0 to n equal to -1. And you can certainly form superpositions of these states as well, and they're also eigenstates. And this is a particular superposition. I'm not going to discuss how that superposition is constructed, but it's based on a principle of minimal fluctuations. You see, what happens is that the reason why there's this degeneracy is that the symmetry of the hydrogen atom is not just rotational symmetry, but it has a higher order symmetry, which you can associate with the fact that in elliptical motion, the major axis of the ellipse is stationary. This is a point that was already observed by Isaac Newton and rediscovered numerous times, and sometimes called the lens vector, because always the last guy who discovers anything gets all the credit. Lenz is the last guy who, got credit for this idea. Laplace knew about it and so forth. But that means there's an additional symmetry. And the symmetry of the hydrogen atom is not O3, which is the symmetry of pure rotations, but it's actually O4. And so this is an O4 solution, which you can get by a suitable rotation in the four-dimensional space, but we will skip that here. Now, here's what happens if you now take a solution like that one, and now, of course, that's a stationary solution. If you want to get a time-dependent solution in quantum mechanics, all you have to do with stationary solutions is you take a suitable linear superposition, and here is the linear superposition. This is what you get initially, and now this wave packet is set in motion, and it is rotating counterclockwise. Notice this is all in units of the Kepler time for the orbit. Notice that at half a Kepler time, the initial state appears at the other end. I mean, remember that the central force is here, and the initial state that you have appears at the opposite end, half a Kepler period. Notice that contrary to all the intuition that goes around that wave packet spread, in fact, this wave packet is actually becomes more concentrated, which you would expect if you have a bunch of particles in the orbits, that when they go halfway around, they slow down, and so they congregate. So quantum mechanics is doing just what you expect classical physics to do. Okay? If you don't mind, I'd like to keep a coherent talk. If you have a question, I'll be happy to answer. But I like the comments to discuss it later. So if you have a question?
Yeah, it's a question. So at your initial time, you had some probability distribution there.
The initial time here is a superposition of the wave packet.
Right.
But they have different phases.
So and then your final time, it looks like it's...
This is the final time.
Right. It looks like it's spread out.
Yeah. Excellent. Yeah. You notice that if you now continue to go around the wave packet, however it does spread, this is one period, one Kepler period later. You're quite right. One Kepler period later, the wave packet has spread, just like the intuition, the arguments of initial arguments over lengths predict.
So
now, yes.
So it will spread more in the second Kepler period?
And then if you keep going, it will spread more and more. But up to then, as the spreading continues, I will soon show you that this spreading has a completely simple classical explanation. Now, where does wave mechanics really come in? And it comes in a very, very interesting way, an unexpected way. For me, it was unexpected. When I did all these calculations, I knew nothing about what to expect. And of course, when you see it afterwards, and that's why calculations are so helpful, then of course everything becomes clear. As if you go around once more, notice that you're going counterclockwise. It will be continuous spreading. So here's the head of the wave packet. Here's the head of the wave packet. Here is the tail. Now eventually, no matter how big n is, eventually the head of the packet will catch up with the tail. A famous diagram that Joel will like very much appears here. And now you really begin to get quantum behavior, because classically nothing special happens when the head of the distribution meets the tail, but in quantum mechanics the behavior is completely different, because you have basically an interference of a wave function with itself, and you have the famous superposition of amplitudes, and you get different behavior, and unexpected behavior that I will discuss in a moment. Yeah, in fact, here is a very simple example that requires this is an example that requires not for you to be a clever calculator, but just if you know how to program, you can write down a program to solve the Schrödinger equation in a 1 over r² field. Do it in 2 dimensions, because you don't really care about the subtleties in the third dimension. So do it in 2 dimensions. And now you say, suppose I start with a, oops, no, I don't want to change this. Let me go back. Suppose you start with a wave packet, which is simply a Gaussian wave packet with a certain, of course, delta x, delta t, I mean, a uncertainty in position and momentum according to quantum mechanics. So it's a quantum mechanical wave packet, but I set it up in motion. Okay, I will set it up in motion. Here's the center, it's poorly indicated, but here's the center of force. I set it up in motion with a velocity perpendicular. And the velocity or momentum is precisely what I need classically for it to go around in a circle. So I take the initial conditions to send this wave packet into a circular motion. And, you know, crank away your solutions. And surprisingly, this wave packet, I mean, you might be a little surprised that this wave packet, well, this is all quantum mechanics, solving the Schrödinger equation numerically. A quarter of a Kepler type, the distribution looks like this. Shocking, you know, absolutely shocking. And then it looks like this, and then after one complete Kepler type, this is the solution. Completely unexpected, right? Completely difficult to understand, right? Not at all. Suppose you take a purely classical distribution. In this case, I took 6,000 particles, distributed according to the same initial conditions, but now obeying Newton's equations. And I set them in motion. And lo and behold, I get something that looks similar. The reason, of course, is that these particles, if they're not at one point, but they're distributed, they all move for different Keplerian periods, and rapidly they spread. The spreading of the wave packet, you can see here, has nothing whatsoever to do with quantum mechanics per se. That's a purely classical phenomenon. If you accept Born's dictum that the interpretation should be the interpretation associated with. Now, last night I played a little bit with my computer, so I want to show you what happens to a quantum distribution when we make it classical. Okay? Let's do that again. This is quantum mechanics. This is classical mechanics. The only place where there's a clear distinction between the two, of course, occurs at this stage, because here the particles are now coming back to the initial state. Some of them have returned, and that is nothing at all. There's nothing special about it. But in quantum mechanics, you see that the distribution now is very complex. So here's quantum mechanics when there's interference, and you see that there are peaks and all sorts of garbage here, which needs to be interpreted. But that's because the head of the wave packet has now interfered with its own tail, and so quantum classical divide, of course, occurs. It depends on your quantum numbers. Here the quantum numbers are n equal to 40, and they occur within 1 Kepler time. In the case of the moon, you know, Einstein was famous for inviting people to look at the moon and answer the question, is the moon there? If I'm not looking at it. I mean, even the great Einstein, you know, I'm sure he was joking, but that was a dumb question, because what's the principal quantum number? The principal quantum number is astronomical. I shouldn't say astronomical. It's 10 to the 70 Kepler periods. I mean, it's not even the age of the universe can express how big that number is. So, of course, the moon is extremely well localized, and it's not going to spread. Neither are the planets going to spread. Quantum mechanics will predict exactly what classical physics predicts. Everything will be identical. But the main point is there's no quantum classical divide whatsoever in this problem, because the transition from the quantum to the classical domain depends on your quantum numbers, and if they are small, they occur, and in fact, we will see experimentally that this is indeed the case. The experiment was done in Rochester by Stroud and his collaborators, and this is a fancy equipment, but basically what it does is to, where is the oven? You have an oven where you have the atoms, oops, the atoms located in this oven, and you send a laser pulse to excite the electron to a prescribed high-level state. They went up to states of the order of n equal 100. And then you send the second pulse, which is cleverly delayed by this, essentially by mirrors here, which you can move around. You send the second pulse to find out where the electron is after it's been excited. And here's the real apparatus. And what you see, in fact, is a series of pulses that show that the, let me show you the graph. This shows that the wave packet is moving in Kepler periods. This is the number of orbits. But there's something very peculiar that happens after there is a interference phenomena. You might say that you might expect interference of the tail and the head to lead to some mess. On the contrary, it leads to beautiful new phenomena. What happens is that it leads to what are essentially revivals of the initial state, but they occur now, note that at Kepler time, for instance, the first revival occurs a half to Kepler time, and then there are numerous other revivals, all of which can be calculated, and we calculated them very precisely. So it's in complete agreement with the theory. I don't have time to discuss this, but again, you're now in the quantum domain, and there's no simple classical description of this domain because it's the way that the wave function is behaving. Now, in the last, I will take only 5 more minutes and then open for discussion.
Can I just ask one question before you go to the Bohm?
Yeah.
That's a very beautiful calculation and experimental results that you report. But I think you're misunderstanding what Einstein meant by his remark about the moon. Einstein's remark seems to me completely at right angles to all of this.
Yeah.
Einstein was, of course, aware that the wave function of the moon didn't spread appreciably in between times that people looked at it. If he had been a little more careful, I don't know exactly who reported this, I take it what he meant was, do you really believe that the moon wasn't there before anybody looked? And what he meant by that was, if you just evolve the Schrödinger equation from the Big Bang, okay, if you evolve the wave function from the Big Bang according to Schrödinger's equation, and if you take conventional ideas about the collapse of the wave function when people make a measurement, before anybody looked, the wave function of the universe wouldn't have even remotely been an eigenstate of the position of the moon, or even of the existence.
Let's discuss that. Let's discuss that at the discussion. I
Okay.
prefer not to answer now, but I will answer your
Okay.
comments. Let's not put into Einstein words that he didn't utter, or thoughts that he didn't express. I mean, explicitly. I mean, he said things in correspondence. But so now let me just go to Bohm. I call it the Broglie Bohm. I was reminded that the Broglie, in fact, had the same idea of a guiding wave, and he expressed it. So the Broglie and Bohm both had the same idea of, and this is straight out of, I like to, as a historian, I like to go to the original manuscripts. There are just numerous papers. Right now there's a whole set of new papers in the American Journal of Physics, which you can read about what is now become a new development called Bohmian mechanics. But the simple idea of Bohm and the Broglie was that there were three principles: that psi is a field that satisfies the Schrödinger equation, that the particle momentum associated with this wave function is described by the gradient of the face of the wave function called S, and then P of x, of course, is the square. You've heard numerous talks, so I don't have to explain what the idea was. Now, I'm going to go here successively to my problem with Bohm. You have a guiding field, which is a solution of the Schrödinger equation, that has an amplitude, we call it R, let me call it R, usually, and S is the phase. And now you say the particle velocity associated with this amplitude is described by the gradient of this phase divided by the mass of the particle. And you've seen beautiful pictures of integrating this equation. For example, in the two-slit experiment, you get a nice picture, you see everything, the interference patterns and so on. And I believe that's absolutely correct. In hydrodynamics, we call that what's the name of these lines that follow?
Streamlines?
Streamlines. I call them streamlines. The streamlines have to look like that. you know, because you're essentially expressing the content of the wave function. So what we see when we see those streamlines is expected because that's the way such a function evolves. And it's a good way of, but the problem is to assign the streamlines to velocities of actual particles. And I'll just give you a very short comment of why I think there are problems. I looked at the lectures and video. I had some problems. Maybe it was pointed out, maybe it wasn't. But the problem I'm going to bring up, if it was pointed out, fine. If it wasn't, I'm very surprised. You see, the momentum, you know, since we teach physics, you know, everybody says momentum is mv, mass times velocity. At least, all of this, of course, is non-relativistic physics. So we're talking about non-relativistic physics, non-relativistic quantum mechanics is Bohm. So momentum is mv, velocity is here. Now we have a problem. Anybody know what the problem is? The definition of momentum does not correspond to quantum mechanics. Why? Well, calculate the average value of the momentum for a given wave function. Okay? And lo and behold, the average value of the momentum indeed corresponds to Bohm, namely the gradient of S, which is the momentum at a given position, and then you calculate the probability of being in the position and you integrate, you get exactly the result of quantum mechanics. Bravo. Are you with me? Because now comes the shock. The shock that's not presented. Calculate p squared. I mean, you need to know what the average value of p squared is because that gives you an idea of the distribution. And it's an elementary calculation that if you calculate the average value of p squared, you're not going to get the average value of gradient of S squared. You have a problem. I know this will be the subject of our discussion, so let me finish in a few minutes, and we will be discussing that. Now, I know there are answers to this, and we're going to hear about them, but let's just say that this simple-minded guy has problems when the average value of p squared in quantum mechanics is different from the average value of p squared in Bohmian mechanics. And I've talked to a number of non-Bohmian physicists, that is, you know, my colleagues, some of them pretty bright colleagues like Tom Banks and others, completely unaware of this problem. Now, I expect the Bohm people to be aware of it. And Bohm himself became aware of it, and he introduced, in one of his papers, early papers, introduced something which I guess is no longer in fashion, that in addition to the velocity, the regular velocity, there's some kind of fluctuating velocity. We call it osmotic velocity because in analogy with Einstein's theory of osmotic particles suspended. And so he said, well, you know, there's, in addition to the regular uniform velocity of my particles, there are some fluctuations, which then account for everything. I have a feeling from reading recent papers, which I have, and so forth, that this is out of fashion, but we will have discussion about it in a few minutes. Let me finish by, as I said, I always like to consider the simplest cases, following Newton's dictum that before you work on complicated problems, work out the simplest example. What's the simplest example in Bohmian mechanics that you can solve is, of course, the motion of a free particle. And how does that look like? Well, you have to calculate S for a free particle. And by this I mean, of course, the wave function associated with a freely moving particle, a Gaussian wave function. Because you need to localize it in position and in momentum. Now what's the equation? Here's the equation. The rate of change, the velocity, the rate of change of position is given by a highly nonlinear dependence on position and on velocity. Okay? So the particle, the simplest problem that you can think of a free particle, no forces, in Bohmian mechanics interpretation, that particle is accelerated. In fact, there are lots of absurdities. The initial velocity at time t equal to 0 of that particle is, no matter where it's located, at time t equal to 0, the velocity is the initial velocity, or mean velocity. So I have problems.
For which wave function?
What?
Which wave function did you take?
The Gaussian wave function. I just expressed what S is for the Gaussian wave. This is a solution. This is a solution of Schrödinger's equation. And it depends on the choice of the mean velocity, okay? And I forgot to tell you what tau is. I'm afraid that I may have left it out on my slide, which is very stupid. Sorry. That comes later. I'm sorry, I left out tau, but tau is determined by the mass and other properties. Very important to say what tau is, but I left it out on the slide. So this is the S, and the point is, and by the way, of course, it shouldn't come as anybody as a surprise who have heard that in Bohmian mechanics, there is, in addition to the classical forces, there is also a Bohmian non-local force, and this acceleration can be attributed to this non-local force that has appeared. This corresponds to people who take the first order equation. You see that in Bohmian mechanics, you really have only a first order equation that relates velocity, the derivative of x with respect to t. So it's a first order equation, but if you take the derivative of the first order equation, you get an equation for the acceleration, which then looks like a classical equation of motion, except for this Bohmian potential. I have enormous problems with doing that because you can't convert the first order equation to second order equation and not expect to get some nonsense out of it, because initial conditions now, in the second order equation, you have initial conditions, arbitrary velocity and position. However, in the first order equation, the velocity is predetermined by the position. And then, of course, you say, well, what happened to the uncertainty principle, particularly in the simplest case where the initial velocity is a constant, seems to throw out the uncertainty. This is a good place to stop. So, thank you. All right, so go ahead.
So I have two remarks. First of all, about the point about Bohmian mechanics. Every word you say is true, except for the perception that this amounts to anything in the neighborhood of a problem. Here's the situation. What you're pointing out, you have in Bohmian mechanics a completely deterministic theory. It predicts the position, given the initial positions of all the particles and the initial wave function, it deterministically gives you the wave function and the positions of all the particles at all later times. You recover the quantum mechanical probabilities by starting with a probability distribution over the positions of the particles. Good. What's being pointed out here is that the results of the kind of physical setup that we're used to referring to as a measurement of the momentum. Okay. These results are predicted, that is, the position on the pointer of the momentum measuring device is predicted by this theory. You recover the Bohm rule probabilities as to where that pointer is pointing, so on and so forth. What you're pointing out here is that the probabilities about that the position of such a pointer on the kind of object we're used to calling a momentum measuring device at the end of such a measurement is not necessarily going to be equal to the mass times the rate of change of the position of the particle. This is absolutely true. Presumably what we're concerned about is not preserving those algebraic relations, but getting the correct predictions about where the pointers on those measuring devices are pointing at the end of those experiments. Vis-a-vis those predictions, we have a theorem that says that the Bohm rule about the probabilities of the positions of the pointer on the momentum measuring device are going to be correct. The fact that it turns out that this doesn't preserve the relations that we're used to from classical mechanics between mass and velocity and momentum, why is this supposed to be a problem? The point of physics is to get the right predictions about the outcomes of experiments. Nothing is being raised here to dispute that the theory does that. Yes, it fools around with some of these algebraic relations. So what?
So, I know we had lunch together. I think you're entitled to your opinion.
Well, no, but wait,
I think in quantum mechanics,
is your opinion?
I've taught physics, for half a century, and I learned it from some pretty good people. And if you say P is equal to mv, and it's the same in both quantum mechanics and Bohmian, I show you that that's not the case.
No,
you bring up the measurement problem in
I never mentioned the measurement problem.
No, you said measurement of P and so forth. That's of course what Bohm himself does. He says, oh, the actual P is not in V, the actual P is in blah blah blah, it comes out just as in quantum mechanics. Okay. But let me leave it at this. I mean, I'm not going to dispute with you. I agree. Let's agree to disagree, okay?
Well, I just want to understand what we're disagreeing about.
Are
we disagreeing about the claim that what physics is supposed to do is predict the outcomes of experiments? Is that the disagreement?
What we disagree is that in quantum mechanics, the mean value of P squared for the same wave function is not the average of gradient of S.
No, we don't disagree about that.
It is not equal to that, and it should be equal according to all the rules in physics that I have learned. Now in philosophy there may be new rules, but in physics, there is a rule that the quantities that you introduce are the quantities you measure.
But please, just answer my question. Are we disagreeing about the claim that the job of physics is to predict the outcomes of experiments? Are we disagreeing about that?
Let me now answer someone else. Okay, go ahead.
In the equation for psi that you have at the very top of the screen, could you talk a little bit about what R is?
Oh, sure. R, see, psi is a complex wave function. So you can always take a complex number and write it in terms of its absolute magnitude in its phase. So R is defined as absolute value of psi. S is defined as its phase. It's just a conversion of a complex number into what we call polar coordinates. All right.
So R doesn't necessarily have to be a constant.
R is a function of A. R is never a constant. It's a function of A. Sure. Now, please.
Yeah, let me just try to say something maybe about the point of Bohmian mechanics or the kind of project it's engaged in. So, when you were talking about quantum mechanics initially, you were talking about the psi that Schrödinger had, and psi obeys the Schrödinger equation. When we want to get predictions out of that theory, we use the Bohm rule, right? We talked about Max Born and the statistical interpretation.
I call it the Bohm interpretation. At this point, you know, this is a very modest thing. I'm just talking about how, from the very beginning, there was a question of interpreting the meaning of psi. And Bohm gave an interpretation for that meaning, that psi squared is the probability of finding the particle with coordinates x and t. Okay? That was his interpretation of what the meaning of psi is. Nothing to do with, you know, fancy measurements and, you know, blah, blah, blah. This is just elementary physics. What does it mean? Okay, well, what is your question?
Well, so, so that's one idea about maybe what the basic rules of quantum mechanics are, the sort of postulates or something that have to do with the Schrödinger equation inside. Bohmian mechanics puts forward a different idea about, it's really a different theory, you might think. A theory that's supposed to get some of the same empirical results, but it has different fundamental rules. The rules is there's psi, there's a Schrödinger equation for psi, there's also particles with positions, and there's the guidance equation gives you the velocities as you put on the board. Now, when we have a new physical theory on the table, the normal way that we test physical theories against each other is by looking at their predictions and seeing whether the prediction works.
I couldn't agree more.
Right. You said the same thing in the past. Now, when you have these two on the...
Peddling the idea that we need predictions. Right?
Yeah. Yeah, so now...
And of course, Bohmian mechanics says we make exactly the same predictions.
Right. And so now we have two theories on the table that make the same predictions. Now, I have concerns about the first theory that it might not be very precisely stated, but putting those aside for the moment and saying that they give the same predictions, what do you not like then about Bohmian mechanics? Do you agree that it's predictably successful? It predicts everything that we see from...
What I don't like is this equation.
So it's something about the structure of the theory.
This is what I don't like, okay?
But what if the theory just didn't even have anything called momentum?
If you say grad S is the momentum, and I take the average...
You don't have to say that.
What?
You don't have to say that.
Wait a minute. You don't have to is a, you know, this is very complicated.
It's a theory of position.
I told you what Bohm said. He said grad S is momentum.
So
in his theory.
It's a theory about the dynamics of particles, right?
Now, if you are you denying that grad S is momentum?
So momentum is a name. You can give them.
It's absolutely, in a sense, this is a question of terminology.
Yeah.
The theory makes predictions about the positions of things like pointers. There doesn't seem to be any dispute.
Try to explain that to a freshman in physics.
Wait, there doesn't seem to be any dispute that all these predictions are correct. You
Grad,
don't seem to be disputing that all these predictions are correct.
I am disputing that in quantum, if the theory makes the same predictions, y is the average of p squared, which is defined by the canonical
you
way.
are disputing that the predictions are the same?
I'm asking a simple question. I mean, I have it in front here.
But you have a simple answer.
No. Explain why this isn't equal to this.
This is because you're insisting on using a term that just isn't an interesting variable in Bohmian mechanics. You don't seem to be disputing at all that it makes exactly the same experimental predictions. You thought that the task of physics was to make correct empirical predictions. You're not disputing in the slightest the claim that the theory makes correct predictions.
Go ahead.
Plugging the same ones. Can you go to the next slide? The Gaussian, maybe it's the last slide. Okay. Why is that not an... If that statement says that a free particle will accelerate, is that not an incorrect prediction?
No.
This is the equation.
The theory...
The velocity of the particles in this theory are not uniform velocities. They are accelerating.
Absolutely.
We saw, by the way, in the correspondence that Bohm gave, not in the interpretation of Bohm, which is with an H, but Born, which is Rn. In Born's interpretation, the particles, you can do the same problem. You can do the problem of uniformly moving particles, which I didn't discuss, and you find, guess what? Surprise, surprise. The distribution behaves identical to quantum mechanics. expressed just like classical and quantum mechanics agree completely, where each particle moves at a constant velocity, just as your classical intuition would make it do. On the other hand, here, if you describe the simplest of all problems, you already have something funny, namely that the particles are guided by a wave function that makes them accelerate.
Okay,
Could you let someone else also talk?
He asked a question that you're not
let him talk, okay?
Yeah. Why isn't this just Bohmian predicts free particles accelerate, free particles don't accelerate?
Right.
Bohmian theory is wrong.
Excellent.
I didn't say Bohmian theory is wrong. I say, is that interpretation that you want? I mean, I gave you beautiful correspondence between classical and quantum mechanics for particles that are freely moving, okay? If you want to have a wave packet without external forces, the wave packet spreads in exactly analogous way to the spreading of a classical ensemble. You do have to do one little thing for classical mechanics that it doesn't have. You have to impose initial conditions, that is, uncertainties in position and momentum that correspond to the Heisenberg uncertainties. Now, those you can't get out of classical mechanics. But if you impose those initial conditions, the future evolves beautifully according to classical behavior. You don't need a, external non-local potential and all the apparatus that you have in Bohmian mechanics. Are there other questions? Yeah.
So you're saying that what you've given us is aesthetically more preferable, not that it has. That's what you're saying, right? Aesthetically, we should not like.
See, I'm very sorry, but my hearing isn't the best. So, do you mind repeating the question?
So what I just heard you say was that I should prefer what you're giving to us because aesthetically it's more appealing, or something like that. Not that what you're saying.
I'm presenting a traditional point of interpretation of psi, which was introduced by Bohm. Before, Bohm had this idea even before there were any detailed calculations. So we realized in scattering theory, which we haven't talked about, we needed an interpretation like this. And I'm just saying, what's the problem? Here's a perfectly good interpretation, and we understand the quantum classical.
Right. So you're saying why do we need another one? You're not saying that.
You can say, okay, I don't like this interpretation. I prefer this other interpretation. And
but you're not saying that scientifically there's a problem or something like that. You're just saying it's not necessary or not preferable.
Well,
because
I have problems when I derive the most elementary equations, such as the relation between the average of p-square and quantum mechanics, and I derive it in Bohmian mechanics, and I get different answers. I have a problem with that. Never mind mechanism, never mind. I have a problem. I have a problem with interpretations that lead to apparent discrepancies.
Are those discrepancies experimentally verifiable?
Yeah,
These discrepancies that you refer to, I'm trying to understand if those are discrepancies that can, in principle, be determined empirically. Because then that would be a cause.
No, the answer is that I've tried to understand. Bohm realized all these things. He was not dumb. He realized it didn't work. So then he said, he pushed the problem in another direction. He said, when we do measurements, that's in the original paper. I don't know what all his successors said. In the original paper, he says, when we do measurements, we measure a different quantity, that's P. In the quantity that we measure is, of course, identical to the quantity that you have in quantum mechanics. So Bohm resolved the issue by saying, well, the measurement of P will resolve the discrepancy. We'll never get anything that's different. Well, You like that? Fine.
No, I'm trying to understand exactly, because so in the case, in what that seems to be saying to me, and I'm not a physicist or a philosopher, is that if you were to do a series of measurements, the P that's representing the momentum operator will give you the right answer, but that on and that's a statistical statement about what you'll see in measurements, but that what we're used to thinking of as M times V isn't really related to that in the same way.
Absolutely, absolutely.
Right.
You said it very clearly.
So how
I'm surprised you can see clearly what we're talking about without...
So what would be the analogous statement for this problem? So there were two problems. One was the one about P equals mv and the momentum operator. Now on this slide I'm having a little bit of trouble understanding. So I can see that you've derived a result where for a free particle the velocity isn't uniform.
Right.
What experiment would we do to determine if this is a problem experimental? That what experimental results? Or is this also an artifact of the fact that when we do measurements we're going to get statistically the right answer, but that individual paths...
I mean, this sort of thing will give you perfectly beautiful streamlines.
Right.
And the sense of hydrodynamics. Quantum mechanics, the streamlines have to be Bohmian, because that's the mathematics. The problem is to interpret these streamlines with the actual position and velocity of physical particles. The canonical interpretation in quantum mechanics is that position and momentum. See, particles have mass, charge, so the idea that, you know, before you do measurements you have nothing is nonsense. Particles have charge, they have mass, invariant quantities. However, position and momentum in quantum mechanics is not a given. And you have to set up an apparatus. And the apparatus you set up to measure the momentum will not give you the position and vice versa. And that, of course, was already understood by Bohr. The V that's here, whatever you want to say, it's not a measurable quantity. It's not a, because this theory says the position and the velocity is fixed. But
why don't you answer?
You're going to measure it the same way that you measure it in quantum mechanics. You're going to get the same answers.
Look,
is this
related?
related?
Ask the same question.
I'm sorry. Let him speak. Okay, give a chance to someone else.
I could be completely off the mark, but is this?
No, you're quite on the mark.
Is this the same as, or is this related to the streamlines that Ward showed for the two split
exactly,
experiments?
it's exactly.
So in that experiment, each of those paths that correspond to streamlines has accelerations.
Sure.
But we don't worry about that in the in the
whether
traditional view.
The streamlines give a beautiful representation of the evolution of the wave function. Just like the streamlines give a beautiful representation of a fluid.
But am I supposed to worry about?
I mean, and you say the streamlines, you can actually see them if you put little, light pellets on the fluid. You see the streamlines too. But the streamlines in the fluid won't tell you anything about the motion of the actual particles in the fluid. And I think the same thing is the case here. The streamlines do not tell you anything about the velocity and position of the particle. Now, of course, here we are in complete disagreement with the Bohmian mechanics, who say, no, these are the real velocities, the real momentum.
Well, I think I follow you, but I think what Bohm would, if I understand Bohmian mechanics, just based on what I've learned this week, I think Bohm would say that those streamlines. Okay, I guess I'm not enough of an expert.
Go ahead. Those streamlines. You're right on track.
Well, those streamlines aren't the actual. I don't know how to relate those in Bohmian mechanics to the actual path that the particle takes.
Very good.
If
you look at the recent literature, you would find as big a diversity of opinions on this as there are writers in the literature. Everybody has its own opinion on what the streamlines mean. And there are specific cases of papers recently in American Journal of Physics where the authors say the streamlines are extremely useful to get insights into physics, and I couldn't agree more. But he says, we say nothing about them representing actual positions and velocity.
In Bohm, you mean, in Bohm's mechanics?
Yeah, these are papers on Bohmian mechanics. There's a group.
Then in Bohmian mechanics, these streamlines are getting projected.
Yeah, they are.
Yeah.
In Bohmian mechanics, these streamlines are the particles projected.
Yeah,
Right.
but that's your opinion. That's not the opinion of everybody who works in the field. There are people who work in the field.
No, I'm just saying what Bohmian
Look,
mechanics is.
specifically, there's a group in Spain. I recently read that paper which specifically says it doesn't matter, whether these streamlines are real particles or not. It's a useful program to integrate these equations, and I couldn't agree more, because they give you significant more information about the content of psi. What is psi was the question that we started with. It was asked by Schrödinger's students on day one. Continues to be asked. But go ahead.
I was just wondering if there was sort of like a paper that you published that with these ideas, this argument is put forward, or is this still something that you've developed recently that you're going to put out soon somewhere? Do you have a published paper where you forwarded this argument, where you put this argument forward?
Do I have a paper?
Yeah, where you you present this argument.
I have a paper on this, which I wrote 2 years ago, and it has been thought it's unpublishable, because no one who, I believe all the referees come from the group that promotes Bohmian. And the one thing that I'm upset about is that they will not allow dissent. So my paper has been rejected by the American Journal of Physics, it has been rejected by the European Journal of Physics, and it's in limbo because, until I get a referee that has an open mind to at least consider that there are difficulties, the answer is it's unpublishable. You can't, in physics like in other disciplines, certain groups are formed, they're convinced in their righteousness, and somehow, but that's my impression, because the referee reports, I can't publish, okay?
Yeah. I find the line of reasoning here to be very interesting, and I would just like to think more about it,
I'll be happy to send you a copy of the paper.
Yeah,
sure, in fact, I should have, I'll put the paper, is there some place
Yeah,
on
I'm
the...
definitely interested.
What?
I'm interested
Yeah,
too.
but is there a place on,
Yes,
on here? Okay.
Yeah, there's a website.
There's a website. I'll put my paper on the website, and I would welcome, comments on what I say in the paper, not on beliefs. My major objection is, and by the way, this is only one. The simplest way of representing is to say p squared. I have half a dozen other ways. Let me, by the way, mention something that the people that believe in the Bohm representation, they always tell you it's identical to quantum mechanics, because everything is in coordinate space, and at the end of the day, it's x and t. Well, ask a Bohmian to do the simplest calculation that goes back to an experiment that was done by Compton in 1922. Namely, you scatter a photon from an electron and calculate the change in wavelength. To begin with, the photon is traveling at the velocity of light. You can't use non-relativistic physics. But even if you could, everything is done in momentum space. There's no question that to calculate the change in wavelength, what you do is, and it's an elementary problem in introductory physics, and what you have to calculate is conservation of momentum and conservation of energy for two particles interacting. There's no position at any time. It's only momentum and momentum exchange. How do you do it? I have no idea. It's the statement that you always are in coordinate space, I think it's false. Yeah, go ahead.
Okay, I think at least two other people that may
Let me get close. Let's say, I have weak hearing, so I want to make sure I hear you.
So I think at least 3 people want to know this. In your opinion, what is the task of physics?
What is the
Task of physics. In your opinion, what is the task of physics? I think at least 3 people want to know.
what is
Task.
the job?
The job of
Oh,
physics.
that's the bigger question.
Yeah.
That's the bigger question to give you a pat answer. I prefer not to. But as I said at the discussion yesterday, physics is not about explanations only. And again, I put on my hat as historian. Let me just be less than brief. I'll say the following. Plato gave a sufficient reason to explain planetary motion, that all orbits of planets have to be circular and uniform. That was his principle of sufficient reason. Okay? Then Ptolemy corrected a little bit by adding epicycles. With Ptolemy, 1,500 years of careful observations, including in Islam and everywhere, there was good agreement. And so the observations agreed with this simple principle. Copernicus came along and said, no, wait a minute, an equivalent explanation is that everything, it's not the Earth that is still, it's the sun. We call that a simple exchange of frames of reference. If the same results, astronomers, no matter how much they observe, couldn't distinguish between the two explanations. Until Kepler came along and Tycho Brahe, and they did things a little bit more carefully. And they noticed a discrepancy. Kepler noticed a discrepancy of a few seconds of arc, and was able to show that the orbit of Mars was not made out of simple epicycles, but could be fit with an ellipse. And he proposed the ellipse. And here's another explanation, which fitted the data a little bit better. Actually, with an extra epicycle, he could have done just as well. His physics of what was happening was an explanation, sufficient reason, planets are pushed around the sun by angels or what have you. Descartes came along and said, oh, I know how this works. I mean, I've got these particles I said a long answer. The particles, there's some gas of particles in vortices, and they are moving the planets around. It was an explanation that was accepted by everybody. Until Newton came along. He said, no, wait a minute. The explanation is different. Newton's explanation. Newton's explanation of action at a distance, gravitation, that's an occult explanation. There's a huge debate going on. So what I'm trying to show you is that physics is well grounded on an edifice, and it's built up, and there are explanations. But explanations you can see can be built up differently. At the end of the day, there's one explanation which triumphs. It's the one that makes correct predictions. It was Newton who gave the correct prediction up to the point where general relativity comes in. So that's the task of physics, is to make, not just to give explanations, but to make predictions for observations that haven't been made. And in the case of Newton, for the next 200 years, people made observations that both terrestrial and celestial, all of which agreed with.
So making experimental predictions is the job of physics.
Ultimately, the job of physics is not only to explain something with equations, mathematics, and so forth, and to see that these explanations conform to the best experiments. But unless there is, in all of this, there is in addition a prediction of something that hasn't been observed yet. This is a big problem for cosmologists, because they have to observe the multi-universe. They have to observe the evidence for it. Until that happens, we can suspend suspended animation. We don't know whether the explanation is correct.
So you don't have a problem with the predictions that Bohmian mechanics make?
I have tremendous problems.
I'm sorry to cut everything short, but the cafeteria will close if we don't stop at some point. So let's thank.
We have to discuss it in private.
Yeah.